Okay, so here we have the next question on the menu today, and it's presenting the following situation where we have a fireman is pointing a is has a hose and is directing water to fire at this target B, a very hot situation, and there are two possible angles at which you could or which the firefighter could spray the water and still hit the target at point B. Okay, and the velocity of the water is 70 feet per second. Okay, cool. So let's just write that out. They use VA. Okay, we'll use VA. I would use VW for water, but you know, we gotta stay with the question and what they gave us, and that is 70 feet per second. Okay, another thing that we want to keep in mind is the acceleration due to gravity. Okay, so gravity is what's causing this water not to just go in a perfectly straight line. So what we're going to need there is gravity, and since this is in feet per second, we need gravity in feet per second, which is 32.2 feet per second. Okay, so the question says that there are two possible angles at which this can be done. And let me kind of describe what would be happening in those two different situations. So here we have our fire person with a hose, and we have a target here. We have 20 meters, no, not 20 meters, 20 feet of vertical distance between them. Let's move that down to make it seem more accurate. And instead of a box, maybe let's just have like a point as a target. Okay, and their separation is a horizontal separation of 35 feet. Okay, so if we wanted to imagine the two possible paths of the water, we got blue, that's a very appropriate color for water. We could have this situation where we're going below the horizontal line, or we could possibly have this situation. Okay, so here we're going to have, let's call that angle U for angle up, and maybe this one, let's call that angle D for angle down. Okay, so we're going to need to calculate these two possible paths, and they're both perfectly valid for putting the water onto this hot target. Okay, cool. So let's proceed by thinking about what's going on here. So this stream of water is going to follow a projectile motion type of situation. Okay, so here's the key: projectile. This is what we want to keep in mind. Okay, so what are some key aspects about projectile motion situations that we need to keep in mind? We know that horizontal component of velocity is constant. Velocity is constant. No horizontal acceleration. Only the vertical component of the velocity is going to be changing. Of velocity will change. Okay, so given this, let's actually break this down into our horizontal side. And our vertical. So our horizontal velocity, let's just call this our x direction. And our vertical, let's call this our y direction. So we have our velocity x, which is always going to be constant. This will be that'll be one thing that we need. We have our horizontal distance, dx, and we have our time that this will take, and time will be the same for both of them. Okay, so our vertical velocity is going to be slightly different. We're going to have a Vyi for initial vertical velocity, because our velocity is going to be changing along the vertical axis. Vyf, our final velocity in the vertical, our vertical distance, our acceleration, which is going downwards, and our time, which will be the same for both of them. Okay, so time is going to be kind of like that bridge between us that helps us keep these two things in line with each other. Okay, so let's express some equations for this. So we know that gravity is going to be negative 32.2 feet per second, because it's feet per second squared. Because we're going downwards. Okay, so that will be one of the things that we know. Negative 32.2 meters per, not meters, feet per second squared. I'm from Canada, so we use meters over here. Okay, our distances, they are given to us from the diagram. So our vertical distance is minus 20 feet. And our horizontal distance, positive 35 feet. Cool. Another thing that we can keep in mind here is that our initial velocity is going to be determined by our angle here. Okay, so our angle is you know, we're pretty much like, if we have this situation and this is our velocity, we know that we're going to have our Vx this way and our Vyi this way, right? So because with the power of trigonometry, we can hopefully see that given the angle, if we cosine it, that will be our horizontal velocity. So cos theta of Vi, so that's our initial total velocity, and our initial vertical velocity is just going to be sine. And let's say that our angles are going to be positive going clockwise. So here is 0 degrees, and here is positive theta, and here is negative theta. Okay, and we'll just need to like keep things in mind, like with the signs and all, just make sure that they agree with our convention here. Okay, so for y is going to be sine theta Vi. Our final velocity, we don't know that quite yet, and our time that it will take, we also don't know that yet, but we know that distance and velocity are related to each other through time. So we know that we can do distance divided by velocity. Horizontal component of the velocity is going to be equal to the time. So we have 35 feet divided by cosine theta Vi, and that will be our time. And because time is the same for both of them, we know that this is going to be the case for here as well. So 35 feet over cos theta times initial velocity. Okay, that's going to be our cos theta on the vertical side of things. Now the only thing that we have left to calculate here is the final velocity, and we know that final velocity, this is our kinematic equation, is equal to initial velocity plus acceleration times time. So if we wanted to make an expression for the y component of this, the final y velocity, we know that it's going to be the initial velocity, so that's just sine theta times vi, and we know that was 70, but I'll just keep writing vi so we kind of know where this comes from, and then plus a, in this case negative 32.2 feet per second squared, times time, which is 35 feet, divided by cos theta vi. Okay, so what we got here is, let's actually sub in vi, so that's for this equation, sine theta times vi, which was 70 feet per second, whoops, not equals, this is going to be minus, and then I'm going to do 32.2 times 35 divided by vi, which is 70. That's going to be 16.1 over cos theta. Okay, nice and straightforward. So now that we have these relationships, we can hopefully find another equation that is representing for t, and then all that will be left is the different theta values, and then we can hopefully be able to solve for that. Okay, so maybe another kinematic equation that we can use is another kinematic. Okay, so another kinematic equation that we should keep in mind is that the sum of the velocities, the initial plus the final velocity, all divided by 2 times the distance, I think, divided by 2 times time, is equal to the distance. Now we know what the distance is, and we just figured out the calculation for the final, and we already knew our initial, so we should just isolate this for time, and then we can sub it into this time expression, equate these two together, and then we can solve it from there. And you might need to do some trig identities, but nothing to be worried about. So to isolate t, you can see that t is just going to be equal to 2d over vi y plus vf y, and these are both going to be equal to the other time, the other way that we calculated time, because the time has to be the same for everyone, is going to be 35 feet divided by cos theta times vi. So 35 feet divided by cos theta vi, and that's the total vi. Okay, so expanding these out a little bit more, we can sub out our initial y's and our final y velocities. So our initial y is just going to be sine times initial velocity Okay, then we have the y component, and we just calculated that here, so that's going to be sine theta times 70. Let's just write 70 sine theta minus 16.1 times cos theta. Yeah, 16.1 divided by cos theta. Okay, and yeah, instead of d over here, we can sub in that number. I know that d, which is the horizontal, I mean the vertical distance, because that was corresponding to the vertical component of it, that's going to be 20 feet. Okay, and 35 divided by 70, that's going to be 2 on the bottom, because VI is 70 meters per second. Oh, I'll write that for there as well. Maybe on the next line. But so here, since VI is equal to 70, we're going to have 1 over, oops, cos theta. Okay, cool. So now we just need to do some math to make this a little bit easier. But you can see that here, that these are the same term. So this is going to be equal to 2 sine theta times 70. And yeah, let's bring the bottom of the right side up to the top of the left side. Okay, so we're going to have 2 times 70, that's 140 sine theta, minus 16.1 over cos theta, whole thing divided by 2, yeah, 2 cos theta. That is equal to 2 times 20, that's 40. Okay, so now we can expand this out a little bit more. So we know that this is going to, sine divided by cos, that's equal to tan. So okay, so this is going to be 140 over 2 tan theta minus 8.05, that's 16.1 divided by 2 over cos squared theta. That's going to be equal to 40. Now, something that we want to keep in mind here is that cos squared theta, the reciprocal of that is equal to secant squared theta, and secant squared theta is equal to 1 minus tan theta, or 1 minus tan squared theta. Okay, so substituting this back into our equation here for that, you can see that that cos squared on the downstairs, that will become the secant. So this will become 140 divided by 2, that is equal to 70 times tan theta minus 8.05. And, you know, the cos squared became a secant squared when we bring it upstairs, and that's equal to 1 minus tan squared theta. Okay, and that is equal to 40. So as you can see here, we just got to expand this out, and then we're going to have a quadratic formula type of situation. Okay, so a lot going on in this question. So the 70 tan squared, that's going to stay as is. Then we're going to have minus 8.05 plus 8.05 tan squared theta minus 40 is equal to 0, because we need a quadratic formula this up. So to organize this a little bit better, 8.05 tan squared theta plus 70 tan theta minus 48.05 is equal to 0. So we shall quadratic formula this. Okay, so my calculator is very cool because it can do this for me, but I'm sure many of you may also have calculators that are this powerful, and if you're really extreme, you can probably do this in your mind because you're just so sharp. I mean, you could do it by hand, but you know, it's not always easy. And anytime you make a mistake, it will definitely hurt a lot. Okay, so my A term is 8.05, my B term 70, and my C term is negative 48.05. And solving for this, I get is equal to either negative 9.33, or we also get tan theta is equal to 0.639. Okay, now taking the tan inverse of this, and the same procedure over here, tan inverse, or arctan, times negative 9.33. So this here is corresponds to theta is equal to negative 83.88, and here this one corresponds to tan inverse of 0.0639, and that's going to correspond to 3.65 degrees. Okay, so the signs are a little bit twisted from what we had originally, but we can see here that given our original situation where we had back up to this diagram here, this guy, either you're shooting it like pretty much straight vertical so that it falls back down onto the target, or you're like pretty horizontal and it falls down. So I would say that it is more reasonable to say that this angle right here, the lower angle, is going to be 3.65 degrees. And the upper angle here is going to be 83.88 degrees. Okay, the signs were a little bit twisted, but I think that was just because, maybe it's because of the sign right here, but sometimes the signs are not going to agree, but the magnitudes are what you should really focus on, because that's what's important here. Okay, so yeah, very long process, but still fun. Very, very fun. And yeah, everything is good. Everything is good. Once you just keep in mind this identity, secant squared is this one right here. Secant squared is equal to 1 minus tan squared. Okay, and that will correspond to this situation and lead you to victory. Okay, cool. So yeah, the above solution here, there is no above solution, so no solution above either 3.65 degrees down or 88 or 83.88 degrees up. Cool.